All right, welcome back. I've got a sweet new headset, and we've been talking about the Fourier series. So, the Fourier series tells us the frequency content of periodic signals, continuous or discrete. If Fourier's story, his work, ended now at the Fourier series, then it wouldn't be entirely useful, right? And the reason is, how often do we actually have periodic signals in practice? So, the Earth goes around the sun. That could be a periodic signal. You can build a circuit and apply a sine wave from a function generator. That's a periodic signal. But even in the strict sense, these are not periodic because in the strict sense, a periodic signal must have started at infinity, meaning it has no beginning, and it has to go to infinity, meaning it has no end. So even the Earth around the sun is a little ambiguous, and a function generator, you push start and you push stop. So these things are only approximately periodic. And in the previous video, I gave a demonstration, and I pulled a fast one on you. We used an image, and we used an audio clip. And the image was certainly not periodic. Behind me here, I have an approximately periodic image. So you see that image there. So how often do we actually have images that are tiled like this that we want to process? Almost never, right? And let me play you an approximately periodic audio waveform. Right. And so how often are you listening to music like this that you want to process? Almost probably never. It's safe to say never, I would think. Anyway, so we need to extend Fourier analysis to aperiodic signals. So let us begin to discover how we can do that. Okay? And for right now, we're just going to look at a square wave, and then in the next video, we will generalize it to other waves. But first of all, so let's understand the point here. The point is to capture the frequency content of signals that are not repeating. So you might say, well, how does a signal that does not repeat have frequency? Well, if you say something like, "Hey Alexa," or whatever, your waveform might look like this. This does not repeat, right? So, but still, there seem to be frequency components in this waveform that I've drawn, even though it does not repeat. And in the same sense, we're going to find the frequency components in this square pulse that does not repeat. Now, I've got an x sub t of t, so this is a square pulse that does repeat. It's got a pulse width of 2t1 and a period of t, and then of course related to that is x of t, which is just a square pulse that does not repeat. Okay, now we know how to find the frequency content of xt, the periodic signal. We've done it. It's the Fourier series. The Fourier series is given by ak equals 2 sine of k omega 0 t1 over k omega 0 t, where where omega 0 is 2 pi over t. We've done that. Now, this is the genius of Fourier right here. He says he recognizes that his contribution to science is not particularly useful, and he considers, how can I analyze the aperiodic signal using what I've already done? And he says maybe the aperiodic signal is periodic, you just haven't waited long enough. That is, maybe we can consider the aperiodic signal as being periodic with period infinity, right? Imagine taking this xt and the period becomes infinity. So this next repetition goes out to infinity land, and this repetition goes out to negative infinity land. At that point, you would have the aperiodic signal x of t. That's the genius. And so the Fourier transform, continuous time Fourier transform, is the Fourier series in the limit as t goes to infinity. This sounds like a bunch of hooey, or in the land of leprechauns and unicorns, but this turns out to be extremely useful. So let us analyze this square wave, and let's start by the Fourier series then. And if I take both sides and I multiply by t, Then on the right, we get rid of t, which is what we're going to need. And I'm going to view omega 0, particularly k omega 0, as being a continuous variable. Okay, so I'm going to write this as, and I'll draw a picture of exactly what I mean in a second. I'm going to write this as this, where omega is a variable, okay, and then what we're doing is we're sampling. So this is a continuous function in omega, and then we sample at integer values of omega 0, and that gives us the Fourier series coefficients multiplied by t, right? So let's just be concrete with this, and let's make a plot of this guy. Okay, so here's omega, and if I plot this thing, if I made a plot of that thing, this is the sinc function where you have the sine of x over x, and if we're going to run into a problem when omega is 0, but we can use L'Hopital's rule, and we can investigate the limit as omega goes to 0. If we take the derivative of the top, that would be 2t1 cosine of omega t1 over 1, and we plug in 0, and so that gives us 2t1. So the behavior of this thing at 0 is 2t1, and then it oscillates as a sine, but its amplitude goes down versus 1 over omega, and so what you get is something that looks like this. Okay, so that's the plot of this thing that I've circled in green. Now, this idea of sampling from this, first of all, this thing in green is called the envelope. So it's telling us something interesting here, but we'll get to that in a second. So now, to get the Fourier series coefficients, I plug in, okay, the 0th harmonic, so that's this height. Then I plug in k equals 1, so whatever omega 0 is, then that might be the height, and k equals minus 1. So what I'm doing is I'm finding the Fourier series coefficients by sampling from this envelope, right? So these blue bars are giving me the Fourier series coefficients. Now, remember we said, and this was still all relating to this guy, the periodic signal. But then we said that if we take the limit as t goes to infinity, that periodic signal becomes the aperiodic signal, right? So let's consider that limit now, and let me ask you, what is the spacing of those bars? What is the spacing? So this guy was 0 omega 0, this guy was 1 omega 0, this guy was 2 omega 0, this guy was 3 omega 0. So the spacing between those bars is omega 0. And omega 0 is 2 pi over t, right? So what happens to that spacing in this limit? What happens to the spacing in that limit? The spacing goes to 0, right, in that limit when t goes to infinity. So that means these guys become more closer and closer, and I don't really mean the area, but I mean the Fourier series coefficients in the limit start to form that exact continuum, right? We start to sample it everywhere in a continuum. Therefore, it's this continuum that I've circled in green that is telling us the frequency content of this signal. Did you follow that argument? As t goes to infinity, this signal becomes this signal. As t goes to infinity, the Fourier series becomes the continuum, the envelope. Therefore, this envelope is telling us the frequency content of x of t. And that is what the Fourier series or the Fourier transform tells us, the frequency content of signals. Okay, so we've just done this now with just the square wave, but now we're going to go into the general case. We don't want to just be analyzing square waves for the rest of our lives. We want to do more useful things. So let's continue on to the next video.